In this video, we're going to prove the distribution for, or derive the distribution for the sample variance, and we're also going to prove that the t-test statistic indeed follows a t-distribution. And let's jump into today's talk, where we prove the sample variance and the t-test statistic follows the t-distribution. We need some preliminary results first. So let's let x1 through xn be independent, normal random variables, mean, mu, variance, sigma squared. And that means that we're taking a random sample of size n. Let's define the sample mean in the usual way, the sum divided by n. We're going to define the sample variance using the unbiased definition for it, where we divide by n minus 1. Oh, that should be an x bar, dang it, and that'll be corrected in the hard copy, because we're taking the mean minus that. Here, property 1, if we take a normal random variable, subtract its mean, divide by the standard deviation, that transforms it into a standard normal random variable, and that's for every x. If we square a standard normal random variable, we get a chi-square distribution with 1 degree of freedom. And these are all properties that you should know, and we've derived every one of these in a previous video in this playlist. And if you sum independent chi-square random variables, then you add the degrees of freedom. So we're adding in chi-square random variables independent because it's a random sample, so we get a chi-squared with n. We're going to use each of these properties in what follows. Now, property 4, if we look at the sum of the xi minus mu squared divided by sigma squared, and as a reminder, that's a chi-squared with n degrees of freedom right here. We know that. Now let's do a math trick where we add 0. So we add and subtract the same quantity. And then when we square this, we keep these terms together and these two terms. And then we sum them, right? These become this. And the cross product ends up going to 0. And then this squared, summed, we get this piece right here. Now, let's call this Q, this term R, and this term S. Now, from a previous video in the playlist, we know that the random variables R and S are independent because this is a function of the mean, and this is a function of these squared terms, xi minus mu squared. And we proved that those were independent in the previous video in this playlist. So we know R and S are independent, and that's going to play a part in our derivation, in what follows. So let's let the distribution, or the distribution of R, which is this term. Oh, notice the S squared, we divide by n minus 1. So those n minus 1s cancel, and then we're left with that squared term. So these are the same. And we're going to show that it's a chi-square distribution with degrees of freedom n minus 1. Now, since Q is a chi-square random variable, and we know this term is a chi-squared random variable, okay, we'll use the properties of moment-generating functions to solve this. The moment-generating function of Q, which is R plus S, and since R and S are independent, it's the product of those moment-generating functions, which implies if we divide ms to the moment-generating function for S to the other side, we get this term here. But note that Q and S are distributed as chi-squared distribution, with the chi-square distribution with degrees of freedom n and n minus 1 respectively. And we know the moment-generating function of a chi-square random variable, so let's just plug it in. See the n right there, and this is a chi-squared with 1. Same base, so we can bring it up and then rewrite it like this. But this looks like a moment-generating function for a chi-square random variable with n minus 1 degrees of freedom. And since moment-generating functions are fingerprints to a unique distribution, and this is a chi-square, the form of a chi-square, we know that R then has to be a chi-square distribution with n minus 1 degrees of freedom. Now, next we want to prove that this test statistic, x bar minus mu divided by S divided by the square root of n, is in fact the t distribution with degrees of freedom n minus 1. So first, let's rewrite this ratio in this form. And if you think about what we have, so we have the numerator, we have the square root of n, we have sigma, and then square root of sigma squared, so those cancel. The square root of s squared is just s, so we do get these back. And it's kind of interesting, I capitalize that, and that's lowercase. I'm going to make that lowercase in the hard copy. But earlier we showed that the numerator is distributed as a standard normal random variable, and the denominator is the square root of a chi-squared divided by its degrees of freedom. Okay, let's look at that first. If we look at this term here, and if we take out the n minus 1 from this the sample variance and then put it divide by n minus 1, then this piece is what we were calling this, right? And we know that is a chi-squared with n minus 1 degrees of freedom. And then we're dividing by the n minus 1, which is the degrees of freedom associated with that. And we know the numerator and denominator are independent. And thus, that's the definition of a t random variable. Standard normal divided by the square root of a chi-square divided by its degrees of freedom. That's a t distribution, a t random variable. And hence, we've shown that that is a t distribution with n minus 1 degrees of freedom. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.